Okay, folks, Q-1-4, part 2. Alright, so now let's deal with this constant velocity, constant acceleration problem. It's basically T-catch. How do we handle this kind of problem? First, we have to identify who's going to have the constant velocity. So we'll do that one in blue. So here we have 22.35 meters per second, which is about 50 miles per hour, and that's a train. And it passes a stationary car, and the stationary car is, velocity of 0. It's stationary. As soon as the train passes the car takes off on an acceleration of 4. How long until the car catches the train? So at the beginning, let's realize what's going on with the train. Train is always going the same, never varies, never wavers, always the same. So this train has an initial velocity of 22.35 and it has no acceleration. We compare that to the stationary car. The stationary car begins with a velocity of 0, stationary. And it's going to move forward with an acceleration of 4. So at the beginning, these dots are very close together, but it doesn't take long for them to spread out, and eventually he's going to catch him. And when he does catch him, he's going to be going faster than the other car is going. So there's a number of ways to approach the solution to this problem. I will show you those, but let's kind of look and see what they want us to find. How long until the car catches the train? That's T-catch. What distance? This is D-catch. What are the speeds when they are in the same distance? So this is V-catch. At what time and distances will the car have the same velocity? Make a position time graph and a velocity time graph for this situation. So first I'll solve it all with math. And I'll come back and I'll graph it. And you can decide kind of how you want to approach it. So the basis for finding T-catch, and that's the first thing we need to find, is that they will have the same distance at some time in this problem. These guys will have the same distance sometime in this problem. The thing that represents distance is number 3. So what I want to do is I want to set number 3 equal to number 3. So we write down all the variables for both objects. That's what I'm doing right now. D naught plus V naught t plus 1/2 at squared is equal to itself. Then I can put in the variables that I know. So I come up here and I grab what I know, 22.35. That was the initial velocity here. And it started at 0 when it crossed the stoplight, and acceleration was 0. So a lot of these terms kind of go away, and we're just left with 22.35 t. Now as we work our way over to the other side, we've got constant acceleration. So that gives me half of 4, or 2t squared. Starts at rest, so you just get 2t squared. So we're left with kind of this, 22.35 t equals 2t squared. So at this point you can kind of manipulate this to make it a little bit easier to work with, and you can either factor out a t. Of course, I always like just to graph this. And so that's what I'm going to do. We're going to get a smiley face parabola. Oops, batteries are low. That's bad. So we're going to put in 2x squared minus 22.35x. I'm going to look and see what I get for a parabola. I may or may not be able to see where it crosses again. That appears to be the case. So let's just bump up our x max to, 50, just to be on the safe side. And there, you can see it crossing now. Maybe, 50 might have been too much. Maybe more like 20. Let's check this out again. So when it crosses the 0 here is the second time they have the same position. The first time is 0, right? Don't forget you get 2 answers for this. 0 and something else. So I'm coming up here to do my left boundary, which is just below it, and then my right boundary, which is just above it. So it's giving me a T-catch, by the way, of 11.175 seconds. So that's my t catch. Now I can take that t catch and I can plug it into either side. Don't forget these things equal distance. And I can come in here and I can plug these in to get distance. And they should be the same number if we did it right. So a quick check reveals that that is the case. So when I multiply, I get 249.76 here. And then if I do it with the other side, 2 times 11.175 squared gives me the same answer. Since they both gave me 259 or 249, I can be sure that I did this right. So that's my T and that's my D. It also said what are the speeds when they have the same distance. Well, one of those two things is easy. That's the blue. Of course, that's going to be 22.35. That's non-negotiable. To figure out what the speed is of the one with constant acceleration, that requires a magic physics formula. That'd be magic physics formula number 1. And it starts at rest and it has an acceleration of 4. And then we could put in this time that we just found, 11.175, and it can tell me what the velocity is for this guy. So we'll take 4 times 11.175. It tells me it has a velocity of 44.7 when they catch. So V catch is 44.7. Now, if you want to know when they're going to have the same velocity, we can do something similar to what we did before. And we can set number 1 equal to number 1 and put in our known variables. So we have V naught plus AT is equal to V naught plus AT. One of them had a constant acceleration of 4. One had a constant velocity of 22.35. There are parts that we don't use based on the knowns. So basically, if I want to know T, I just take 22.35 and divide by 4. So 22.35 divided by 4 is 5.58 seconds. Now it just so happens that that is exactly half of the time when they caught each other. And that's always the case when they leave at the same time. You always get half. So that's the time when they have the same velocity. Of course, we could then take that time and plug it back into our distance expressions, and we could figure out what they would be. 22.35 times 5.6 gives me 125.16 meters at 5.6 seconds. And then I can do the same thing for the other one as well, and I can plug it into 2t squared, 2 times 5.6, and then I could square that, and I get 62.72. A quick check reveals that 125.16 is half of the distance when they have the same position, and 62.72 is then half of 125.16. Point being, when they have the same velocity, the one with constant velocity is still in front, and that's half the distance, and the one with constant acceleration is behind, and that's a quarter of the distance. Now, how will all this look in a graph then? And how can we use graphing to basically tell us the same thing? So if we wanted to make graphs for these, we can do that. Let me get rid of that. And I can put them in for these two expressions right here. So 22.35t and 2t squared. This is how we're going to get these things. 22.235x and 2x squared. Now when I hit graph, you'll see that we get our one with constant velocity and then the one with constant acceleration. My window's a little short in the y, so let's pump that up to 80 maybe. I should have known better. The distance is 249, so it's going to take a while to get there. So let's go back to our window again. They intersect at 249 at a time of 11, so let's bump this up to 300. Now we should be able to kind of see what we're after. There we go. So this is my position graph. So if we look here on my graph, constant velocity does this. It comes right on up. Constant acceleration does this. More and more and more and more. And then this is the intersection, so that would make that T, and that would make this D, T catch and D catch. And those can be found using our calculator by doing an intersect. So my intersect here is 249.76 and 11.175. Just what we already knew. No surprise there. Now for the velocity time graph, we'll kind of go through here and turn these off by pressing enter over the equals sign. And I'll create my next graphs. My next graphs came from 1 equals 1. So I had 4x and 22.35. So 22.35, and then I come down and I say 4x. And I look at this graph. There's constant velocity and there's constant acceleration. The window's way too high right now. So maybe I just reduce my window down to a more reasonable 50. Now it looks more like I should on my paper, and I'm ready to draw it. So I have my constant velocity streaking across here, always 22.35, never changes, constant speed. Then I have constant acceleration starting here at the stoplight or 0 and coming up with a straight line. And this intersection here does not occur at t. It turns out it occurs at half t. How could we confirm that? We could calc that intersect again, and I could move over to the intersect and find, yes, indeed, it does happen at 5.6 seconds. So 5.6 seconds is half of that 11.175. So if we want to know our distances then at half t, which it turns out to be 5.6, we can find these distances by turning back on my distance graphs. So if I come back here, I could turn these guys off, and I could turn these guys on. And I can graph it. Remember, I got to adjust the window. Last time I made it 300, I'll make it 300 again. Now it looks more like it should. And this time we're going to pump in a value of, I'm waiting for my parabola here. Oh, I guess it helps if you turn it on. This time we're going to put in a value. So we're going to put in a value of, let's see here, 5.6. Now, there was a more exact answer, but yeah, I know. I'm sure some of you deal with this sometimes too. A value of 5.6, 125.16, and 62.72. So 125.16 and 62.72, which is half D and quarter D. One last thing to do, that's to turn back on the velocity plot. So we turn this on. Remember, this isn't going to really work all that well, so we want to make our window more manageable. I think I did 50 last time. Here comes my constant velocity, constant acceleration. This time we're going to put in a value of the intersection time, 11.17, and see exactly what their speeds are. Of course, this one's 22.35 and this one's 44.68, which is twice the velocity. So at 11.175, this will be 44.68. So I've shown you two ways now to make this happen. Let's go through and put in our different answers. 11.175 would go in here. The distance is 249.76. The velocity of the train when they catch each other, that's easy, never changes. When they catch each other, it's going twice as fast, 44.68. Time when they have the same velocity, that time occurs at 5.6. The train is 125.16, and then the car is 62.72. So that's pretty much everything I might have you solve for on the quiz. Remember, on the quiz, I'm not going to make it tough on you. I'm going to make them leave at the same time. So all this half business will remain true. But come the test, we are going to wait a second And what that's going to do is it's going to move this line up here, which drastically affects t-catch. But what's interesting is the velocity graph is not affected at all. Okay, so we'll talk more about that later when we do the study guide. I hope this helped, and of course good luck on the quiz, and I'll talk to you later. Bye.